Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 9 of Algebraic Topology. Our today's topic of discussion is fundamental group of a circle. So in this lecture we will see what is fundamental group of a circle and we will prove the results. So as we know that we denote circle by S1, and in this lecture we want to compute pi 1 of S1 1. Okay, so as we can see that circle is path connected space. So and we also know that if we have a space which is path connected, which means there is a path between any 2 points x and y, then the fundamental group pi 1 of, let's say this space is x, at x is isomorphic to the fundamental group of x at y. So since this S1 is path connected, so we can take any point and we can calculate the homotopy classes of loops at that point, which is the fundamental group, and it's the same for each and every point of the circle. Okay, so we define S1 to be the set of all complex numbers z with norm of z is equal to 1. Okay, so set of all complex numbers x plus iota y such that this norm, which mean x square plus y square square root is equal to 1, which means set of all points in plane whose distance from origin is equal to 1. Now what's the rough idea of what we are going to do? Okay, so consider a map H from z to z square. So in this case H is a function of a complex variable and it takes complex numbers and it gives me complex number. So it's a function from complex plane to complex plane. But if I restrict my attention to only unit circle, then what are the images of circle, images of a unit circle under this map H? So let's see. So if z is equal to r cosine theta plus iota sine theta, then h of this z or x plus iota y is equal to r square cosine 2 theta plus iota sine 2 theta. But if we restrict our attention to only unit circle, then what will happen? So we know that what is unit circle. So in parametric form this can be written as cosine 2 pi t plus iota sine 2 pi t, and where t varies with values from I, and I is equal to the closed interval 0 to 1. So in other words, when t varies from 0 to 1, then this theta varies from 0 to 2 pi, and hence we are getting points on the unit circle. So for t is equal to 0, the point is cosine 0 plus iota sine 0, sine 0 is 0, so cosine 0, which is 1, so basically we are getting this point. So starting from this point, and when t varies from 0 to 1 and when t is equal to 1, we are again getting the point. So basically after taking a round of the circle, we are approaching at the same point. So that's how we get a circle, and this is the parametric form of the circle. Now the image of S1 under H is given by this. So basically as you can see that when I take the power of z, then the angle is multiplied by 2 and the radius is unit, so there will be no change in this case, in the case of circle. So basically the angle is doubled here. So what's the effect of this thing, which so H of S1, the image of S1 under H is this, and what is the effect on the circle of this H? So as you can see that when t is equal to 0, we are again getting the same point. Okay, so there is no change. But when t varies to 1 by 2. So when t reaches the point 1 by 2, then we get the point cosine 2 pi plus iota sine 2 pi. So in other words, when t varies from 0 to 1 by 2, then we complete the whole circle. So what about these values? So because t varies from 0 to 1, so after 1 by 2 the circle start repeating itself, and we are once again repeating the circle points and again reach at the same point. So basically if we have a unit circle in plane, then the image under H of this circle is going to be the unit circle, but we are circling the circle twice. Okay. Now intuitively H is not homotopic to constant map. Okay. Now we will see a way to distinguish between these two maps. So now we are going to have a mathematical background of these two ideas, how this H, which is circling the circle twice, and this map, which is just taking every point to the identity, to the unit, basically they are not homotopic. Now we will see how we can do that mathematically. So as a rough idea of the plan, consider this integral. Okay. So we are going to call this winding number, and we will see why this is called a winding number. Okay. So consider this integral 1 over 2 pi iota, and this integral is taken over f dz by z, and where f is some nice parameterization of the circle. Okay. So this circle denotes that we are integrating on some simple closed path. So where f is a parameterization of the circle. Okay. So in particular we can take this parameterization f of t to be e raised to power 2 pi iota f tilde for some real valued function f tilde. Okay. So as we can see that these are going to be the points of the circle again. Okay. Because the values cosine 2 pi iota f tilde, so they are all okay. So cosine 2 pi f tilde plus iota sine 2 pi f tilde, so they are going to be points of the circle. And as we vary, so let's say this f tilde is as variable t, then as we vary the values of t, then we will be getting some numbers, and we will be calculating this expression, and these are going to be the points on the circle. Now let's evaluate this integral. So we have taken f of t to be e raised to power 2 pi iota f tilde. Okay. So what is dz then? So dz is equal to e raised to power 2 pi iota f tilde and 2 pi iota f tilde prime, because we are using the chain rule. So for example, the outside inside rule says that just take the derivative of outside function, which is just this, because the derivative of e raised to power x is just e raised to power x, and then the inside function is this function, so we are taking the derivative of this, hence the integral becomes this. So we can write down this as z into 2 pi iota f tilde prime. So z will cancel out with z, and 2 pi iota will cancel out with this 2 pi iota, and we will get f tilde prime of t dt, and when we will integrate it, then we will get f tilde of t 0 to 1, so basically f tilde of 1 minus f tilde of 0. So in particular, if we take f tilde of t to be 2t, then f of t is equal to 4 pi iota t, so we have this winding number is equal to 2. We have also seen that this H is basically taking a unit circle and circling it twice. Okay, so H of S1 is unit circle, but we are circling it twice. So in other words, we are winding the circle twice, and we also get this W of F to be equal to 2. So that's why we call W of F to be the winding number, because it gives us that number, the number how many times we are circling the circle, and the number with which we are winding the unit circle. Okay, so similarly, if we have f tilde is equal to mt, then function f of t wraps a circle mod of m times. We are taking mod because this m could be negative as well. Okay, and the winding number is mod of m. Okay, so we have seen a way of looking at the functions whose values are coming on a closed circle. Okay, so function, and we have seen that there is a winding number involved. Okay, and this function f, which is a function from I dot to S1, okay, has a related function f tilde, and basically it's this function f which we are discussing, but the winding number is obtained in terms of f tilde. Okay, but we have seen that this function f is any function from I to S1, and this seems like that this is a very particular case of f, because in this case we have taken a very particular form of f of t, that f of t is equal to e raised to power 2 pi iota f tilde. But we are going to see that this is not the case, and we will see that every function f from I dot to S1 can be written in this form, and hence we can calculate the winding number using this function f tilde. Okay, so in the same way as we have calculated in this way, that the winding number of f is equal to f tilde 1 minus f tilde 0, which is equal to 2. Okay, so why f tilde 1 minus f tilde 0 is equal to 2? I'm sure you can easily see it, because f tilde of 0 is 0 and f tilde of 1 is 2. Okay, so now we are going to see the general situation where given any function from I dot to S1 1, and we will see that this function f, this general function f, can be written in this form, and we will be using this f tilde to calculate the winding number, and these winding numbers will define the degree of a function, and which will help us in calculating the fundamental group of a circle. Now a few facts about a unit circle. So this circle S1, which is set of all complex number whose distance from origin is 1, is a group under complex multiplication. So it's a very simple exercise for you, so I'm just leaving it as an exercise. If f of x is one point on the circle, then the point minus f of x is called antipodal point of f of x. So let's say this is the point f of x, then this point is antipodal point. So in other words, this line joining f of x and minus f of x, which passes through origin, so at the end of these 2 points I have f of x, and at the other side I have minus f of x. So these are antipodal points. So similarly, take a line passing through the origin, and let's say this function, this value is g of x, then this value is minus g of x, and these are antipodal points. So I'm just saying that if f of x is some particular complex number a plus iota b, then this point is basically minus a minus iota b. I'm sure you can easily see that. So similarly, if g of x is equal to a1 plus iota b1, then minus gx is equal to minus a1 minus iota b1. Okay, so these are antipodal points of each other. Now the multiplication map defined by AB goes to AB. So S1 is a topological space, and the product topology is S1 cross S1. So we have a map from one topological space to the other topological space, and the fact says that, which we can prove, which we can easily prove, but this is not going to be part of our course, that this map is continuous map because it's a map between two topological spaces. And similarly the inversion map, because S is a group. Okay, so S is a group under multiplication, complex multiplication, so there will be inverses of elements. Okay, so the function which takes elements of S1 to the inverses of the elements, so this function is also a continuous function, because clearly this inversion function, this inversion map from S1 to S1, so it's a map between two topological spaces. So we can talk about the continuity of it, and the fact says that this map is actually continuous. So the multiplication and the inversion maps are continuous maps in the group of circle of radius 1. Now to understand the fundamental group of S1, we need to understand loops inside S1. Of course we know that what is fundamental group. These are path classes of loops inside S1. So in other words, we have to understand functions of this type. So we have already seen that they define loops. Okay, and where f tilde is a real valued function, and we are concentrating once again on this f tilde, because with the help of this f tilde we can calculate the winding number, we can calculate the number of times we are going to circle the circle. Okay, so we are going to wrap the circle. So we concentrate on functions f tilde with special attention to their endpoints. So because we can calculate the winding number by just evaluating f tilde of 1 and f tilde of 0, and let's go back and see why this is true, because the winding number can be calculated by just the endpoints of this f tilde, the functional value of f tilde at the endpoints of the interval. Okay, now this is going to be our main result of today's lecture. So let X be a compact convex subset of some Euclidean space Rk, and f from x0 to S1 be continuous. Okay, now this S1 is a topological space, and this 1 is basically a point on this topological space. X is some convex compact subset of Rk, and x0 is some point in X. So it's a topological space, so this f is basically a continuous function between these two pointed topological spaces. And t0 is any integer, then there exists a unique continuous function f tilde from x0 to r t0. So this is the real line, and let's say this is the point t0. Okay, so with f of t is equal to e raised to power 2 pi I f tilde. So what does this result says? So this result says that if I have a continuous function between these two pointed topological spaces, then this f tilde, this f can be written as f of t is equal to e raised to power 2 pi I f tilde. In other words, there exists an f tilde between x0 to r t0, and we can also choose this t0. Okay, so this t0 will not be decided, so we can choose this t0 to be any integer. So there exists this map f tilde between x0 to r t0 such that this f function is basically equal to e raised to power 2 pi I f tilde. In other words, I can go from here to here, or I can first go from here to here, and then I can calculate the exponential. So this exp, So exp of x is equal to basically e raised to power 2 pi I x. Okay, so if we first apply f tilde and then apply exp, so if we first apply f tilde and then apply exp, so basically this is equal to e raised to power 2 pi I f tilde of x. So if we go from here or if we go from here, we are going to get the same map. So if this f is equal to this thing, so if we can prove this result, then we are way much closer to our main theme of fundamental group of the circle. So the main theme, once again let me repeat, is that given any continuous function f, so we are calculating its winding number, and we are going to calculate that winding number using f tilde. Let's see how to prove this result. So we have seen that there is a condition on X that it's a compact metric space. Okay, so f is uniformly continuous. So if we have a continuous function from a compact metric space, okay, then to any space y, then f is uniformly continuous. So what is uniformly continuous? So uniformly continuous says that f of x minus f of y is less than epsilon whenever x minus y is less than delta. So remember, there is a difference between uniform continuity and the continuity. So what is the definition of continuity? Let me write it down. So a function is continuous at x naught if f of x minus f of x naught is less than epsilon whenever x minus x naught is less than delta. Okay, so there is a difference between these two. So we, in this case, in the second case, we have fixed the x naught, and we are saying that whenever the distance of x from x naught is less than delta, then the difference between the functional value is less than epsilon. But in the above definition, there is no constraint, there is no fixed radius, there is no fixed center of the interval. So I can just take any 2 points on the interval. Let's say this is the point x and this is the point y. So the only thing they need to satisfy is that the difference between them is less than delta. So the difference between them is less than delta, then f of x minus f of y is less than epsilon. And if I take any other 2 points, let's say alpha and beta, and if the difference between them is less than delta, then f of alpha minus f of beta, this must be less than epsilon. So this is much more a general condition. So in other words, we can say that every uniformly continuous function is continuous, but the converse is not true. Okay, so this is a much more stronger condition than the continuity. Okay, so f is uniformly continuous. So we can have that I can take this epsilon to be 2. Okay, so I can take epsilon to be any number. So in particular, I am taking it 2. So there is a reason for doing that, and so we will see why this is why there is a reason. So if f of x minus f, so f of x minus f x prime is less than 2. Okay, whenever x minus x prime is less than epsilon. Okay, so why we are taking it to be less than 2? Because what is f of x? So f of x is going to be a point on the circle. Okay, because f is a map. Okay, so this f, so let's go to the statement. So this f is a map from x1 to s1. Okay, so similarly f of x prime is going to be another point on the circle, and we are imposing the condition that the difference between them is less than 2, because if we allow the distance to be equal to 2, then we will be also including the antipodal points, because the distance between minus f of x and f of x is exactly 2. So in this case, we are excluding the 2, so that's why f of x minus f of x prime is less than 2, implies that f of x and f of x prime are not antipodal points, they are not opposite to each other, they are not, so I can't obtain f of x prime as minus of f of x. Okay, so this situation is allowed, but this situation is not allowed. Okay, so now x is bounded by Hangul theorem. So what is Hangul theorem? So it says that a subspace of Euclidean space is compact if and only if it is closed and bounded. So x is basically, let's go back to the statement. It says that x be a compact convex subset of some Euclidean space. So x is a compact subspace of Euclidean space, so it means that it must be closed as well as bounded. So the boundedness implies that x minus x naught is less than n epsilon. Okay, so I can find this n such that n into epsilon is basically the upper bound, or in other words I can say that fix this point x naught, and the distance of any point of the space from this x naught is going to be less than n epsilon. Okay, so take any other point, so this distance is going to be less than n epsilon, so this distance is going to be less than n epsilon. Okay, now we can take this line segment joining x naught to x, where x is any point of the space. Okay, now this line segment is going to be contained in the space x. Why is that the case? Because x is convex. So if it is convex, then the line segment joining any 2 points must be contained in x. Now we can take this line segment and we can divide this line segment into n intervals of equal length. Okay, so this x naught, so starting from x naught and then x2, x1, x2, x3 up to so on. So we have divided this line segment. So what is the length of this line segment? X minus x naught. So we have divided this into n parts, so the length of each interval is going to be 1 over n x minus x naught. Okay, so we can also determine these points which are going to be uniquely determined, because the condition is very unique that this line segment is divided into n parts, so that's why these x1, x2, x3 up to xn are going to be unique, and of course this x naught xn is equal to x. Now the difference between xj and xj plus 1. Okay, so take any two consecutive points on this line, so starting from x naught, x1, x2 up to so on, ending at xn. So take any two consecutive points xj, xj plus 1. Now the difference between them is of course x minus x naught over n, and this is going to be less than epsilon. So why is that the case? Because x minus x naught norm is less than n epsilon. So if this is less than n epsilon, then n will cancel out with n, so this is less than epsilon. So if this difference is less than epsilon, now according to our first condition that f is uniformly continuous, and whenever the distance between x and x prime is less than epsilon, then the difference between the functional value is less than 2. So in this case the difference between xj and xj plus 1 is less than epsilon, so that's why the difference between f of xj minus f of xj plus 1 must be less than 2. So one thing is very clear, that if the difference between them is strictly less than 2, then they are not going to be antipodal points. So in other words, if f of x and f of y are antipodal points, then f of x is equal to minus f of y, and which implies that f of x, f of y inverse is equal to minus 1. So they are not antipodal points, so f of xj inverse into f of xj plus 1 is not equal to minus 1. So remember what is this inverse means. So this inverse means inverse of a complex number. Also this inverse is also inverse in the group of S1, and we have seen that this S1 is group under the complex multiplication. Okay, so using above discussion, we can define functions gj's. So what is this function? So these are functions from this space X, so which is our given space with the fixed point with this mentioned point x0. So xj from x to s1 minus 1. Okay, so this is s1 and this is the point -1. So how do we define this function? So gj of x is equal to fxj minus 1 raised to power -1 into f of xj plus 1. So that's how we define gj's. Now we have seen that this output is never going to be equal to -1, so that's why this is a function from x to s1 minus -1. So this point is never going to be in the output of this function. So why this product is an element of a circle? We know that f is a function from x to s1. So basically this f of x j plus 1 is an element of the circle S1. F of x j inverse is element of this circle. So given 2 points, let's say f of x j inverse f of x j plus 1, so their multiplication must be on S1 because we have seen that it's a group under multiplication. So f of xj is a point on the circle. Why the inverse? Because it's a group and the inverses also belongs to S1. So it's a function, gj is a function from x to S1 minus 1. And due to the fact that multiplication and inversion maps are continuous function, and we are using in the definition of gj's, so we are using these two, multiplication and inverse functions, so that's why gj's are going to be continuous functions. Also we have g of x naught, g naught of x naught is equal to I, so sorry, gj of x naught is equal to 1 for all j. So what we are doing, okay, so if we concentrate on the definition of gj, so given any point in x, okay, so this is the space x, any point, so x is any point in the space, so take this line segment, divide this line segment, and from this line segment get the values of xj and xj plus 1, okay, and then basically okay, so this is xj minus 1, this is xj plus 1, so and then use this definition to find the value of xj of x. And of course if you are taking your initial point and final point to be x naught, then the line segment joining them is basically just nothing, it's just a point, so that's why this value is going to be equal to 1. And we can see that if we take xj to be equal to x naught and xj plus 1 equal to be x naught, then this multiplication is going to be 1, okay, because in this case xj, all of these xi's are going to be x naughts, okay, so that's why gj of x naught, which is equal to, okay, so f of x naught inverse into f of x naught, so this is going to be equal to 1 for all j. Using multiplication of S1, we can define the following telescoping product in S1. So what are we going to define? So f of x is equal to this thing, so this f of x naught can be cancelled out with this f of x naught inverse, and similarly these all will cancel out till f of x n minus 1, okay, so these are all will be cancelling out. But what about f of xn? So in the division of the line segment, we have seen that this xn is equal to x, so in other words we can say that this f of xn is equal to f of x. Now consider the restriction of the exponential map from R to S1 to the interval -1/2 to 1/2. Okay, so we have a real line, and on this real line we restrict the real line to -1/2 to 1/2. Of course, if we take this exponential map from the real line to S1, then this map is defined as e raised to power 2 pi iota x, and the output is going to be from the points of the circle, and the input is set of real numbers. But if we restrict this to the interval -1/2 to 1/2, then we will get points of S1 minus this point -1. Okay, so why is the case? Because we can easily calculate the image of -1/2 and the image of 1/2, and this is going to be this point -1, and in this open interval we have excluded those points, so this is going to be a map from this open interval -1/2 to 1/2 to S1 minus -1. So we have taken -1 out of here. Okay, now we have this exponential map from this open interval to S1 minus this point. The above restriction is homeomorphism. Okay, so there exists an inverse, say lambda. Okay, so if this is a map from -1/2 to 1/2 to this circle minus this point, then this lambda is going to be a function from S1 minus -1 to this open interval. Okay, so this composition, we can define this composition. So we have seen that GJs are function from X to S1 minus 1. So in other words, we are coming from X to S1 minus 1, and then we can go to -1/2 to 1/2. Okay, so we can define this composition, and this composition is going to be continuous because GJs are continuous and lambda is continuous because EXP is homeomorphism, so that's why its inverse, which is lambda, is also continuous. So that's why this lambda is continuous, this is continuous, so the composition is continuous. Now we can define this function f tilde in the following way. So we have seen that this composition of lambda and G naught is going to be continuous, and similarly lambda G1 up to lambda Gn minus 1, and we can calculate this function, and these are all continuous, so their sum is going to be continuous. So f tilde of x is a continuous function, and of course f tilde of x naught is equal to t naught, because these are all going to be 0 at x naught. Okay, so these are all 0 at x naught. Okay, so why they are 0? Because g of x naught is going to be 1, and lambda of 1 is going to be 0. So why lambda of 1 is going to be 0? So lambda is taking points of S1 to this interval, and so this 1 is going to be to 0. Okay, so somehow we are starting from here and circling, and so this point is going to be in the middle point of this thing. So we have a required f tilde. Okay, so that was our main object of today's lecture, that given any continuous function from x to s1, there must exist f tilde such that f of t is equal to e raised to power 2 pi I f tilde. But the statement says that this f tilde should be unique. Okay, so how to prove the uniqueness? So very typically we are going to take another function g tilde satisfying this condition, that f of t is equal to e raised to power 2 pi I g tilde. Now define the function h of x, which is the difference of these two. Now what is e raised to power 2 pi iota h of x, which is e raised to power 2 pi iota f of x tilde minus g of x tilde, which is equal to e raised to power 2 pi iota f tilde x and e raised to power 2 pi iota g tilde x. So this is equal to f and this is equal to f, so this is equal to 1. Okay, so what does this imply? So we also know that this is a homomorphism of groups with kernel Z. Okay, so this function has which is basically homomorphism of this group R and this group S1, and the kernel is set of integers, because if you take integers then you are going to go to 0 of this S1, which is 1 of the circle. Okay, so the identity of this is 1. Okay, so for example, take cosine 2 pi plus iota sine 2 pi, then we are going to get just this point. Similarly, take any integer k and you are going to get this point 1. And since e raised to power 2 pi iota hx is equal to 1, so h of x must be integer valued function, because its image is basically 1. Okay, so this h of x must be integer valued. So we also know that x is convex, which means that it is path connected space and hence connected space. So we have an integer valued function h from x to r, so h must be constant function. So if x is connected space, so we already know that the continuous image of a connected space is connected. So in other words, this h, which is going to give me only integers in its output, and which is a continuous function from a connected space, then this image must be only one element. So for example, k. Okay, so because if there are more than two elements, let's say k and k plus 1, then so this set is definitely not connected unless we take the output of h to be only one integer. Okay, so that's why we say that this h must be a constant function. Now we also know that what is h of x naught. This is equal to f tilde of x naught minus g tilde of x naught, and both of these values are going to be t naught. So why is that the case? Because we are taking these f tilde and g tilde to be continuous function between these two pointed topological spaces. Okay, so that's why g tilde of x naught must be equal to t naught. So this h of x naught is equal to 0. So a constant function whose value at one point is equal to 0, of course must be 0. Okay, so hence we can say that f tilde is equal to g tilde, and so we can say that there is a unique f tilde. So what we have proved so far is, given any continuous function between the pointed topological space xx naught to s11, and given any point, okay, so there is no condition on t naught, we can take t naught to be any point, then there exists a unique continuous function f tilde. So this f tilde is the lifting of f, such that this f can be obtained in this way, and we are going to use, okay, so remember that we are going to use this f tilde to calculate the winding number of f. So in particular, instead of taking this x naught, which is so x is a compact convex subset of Rk, so if we replace this x naught with I dot, this be, so if this is a continuous function, then there exists a unique f tilde from I to R, such that this holds. So this I is basically convex compact subset of R1, so that's why we can apply this above lemma over here, and very trivially you can see that everything is in place, and in particular we have taken this t naught to be equal to 0 in this case. Okay, now let's begin with another important corollary of this lemma. If we have a function from I dot to s11, and it's a continuous function, and if it is relative homotopic to g, then f tilde is homotopic to g tilde. Okay, so what is this statement? So it says that if we have another function g from x, so in this case this x is going to be I, and this is going to be I dot. So if I have another function g, and they are homotopic to each other, relative homotopic of course, and corresponding to this f there exists f tilde, and corresponding to this g there exists g tilde. Okay, now the result says that if f and g are homotopic, then this f tilde and g tilde are going to be homotopic as well. Okay, so of course relative homotopic, where g tilde of 0 is equal to 0, so we have taken this t naught to be 0, and f tilde of 1 is equal to g tilde of 1. Now let's see how to prove this result. So I think the proof is not very difficult, so just use the homotopy between f and g to define the homotopy between f tilde and g tilde. Okay, so f, capital F, which is a function from I cross I to S1, is going to be the homotopy between f and g, that is f of x0 is going to be equal to f of x, and when t is equal to 1, this is going to give me g of x. So remember, if I have a function f of x, then this is homotopic to g of x. So if there exists a function capital F xt, so as the t varies, okay, so as the t varies, so t is equal to 0 to t is equal to 1, so starting from this f of x, so we are getting other functions, and we are continuously deforming into the function at the other side, and we have taken this function to be g of x in this case. So in other words, when t is equal to 1, I'm getting g of x, when t is equal to 0, I'm getting f of x. Now since I cross I is compact, because I is compact and I is compact, so there this Cartesian product is compact. So according to above lemma, after choosing this 0 0 as your marked point in I cross I, or as our base point, then there exists f tilde from I cross I to R, such that this holds. Okay, so in this above lemma, I can take this x to be any compact convex set, and in particular I can take to be I cross I, and I can take the marked point or base point to be 0 0, and this is a function from this space to S1 1. Okay, so this is capital F. So according to above lemma, there must exist f tilde to R, and we can take this t naught to be any point, so in particular we can take this to be 0, such that this f is equal to e raised to power 2 pi I f tilde. Okay, so we have applied above lemma to find this capital F tilde. Now what we are going to show is that this f tilde, which is confirmed from our previous lemma, and this f tilde is basically the homotopy between f tilde and g tilde. So why this is the case? So let phi naught be a function such that f tilde of x0 is equal to phi naught. Now phi naught of 0 is going to be f tilde of 0 0, which is equal to 0. So why this is 0? Because we have taken the base point of I cross I to be 0 0, and we have taken the base point of this R to be 0, and we have said that if f is a map between I cross I to S1 with these mark points or base points, then f tilde is a map which will take 0 0 to 0 of f, because this is a continuous function between these two pointed topological spaces, so it must take this point to this point. So this f tilde of 0 0 is equal to 0. Now what is e raised to power 2 pi I phi naught? So this is equal to e raised to power 2 pi I f tilde x0, and by this expression this must be equal to f of x0, but this is equal to f of x, because this capital F is homotopy of f and g. So according to this expression, f of x0 is equal to f of x, so this is equal to f of x. Okay, so basically this phi naught is a lifting of f of x. Okay, so what is f of x? Once again, f is a function from I dot to s1 1. So there exists, okay, so if this is the function f, then there exists a unique f tilde which will take 0 to 0, and that's what phi naught is doing. It's taking 0 to 0, and also e raised to power 2 pi I phi naught. Okay, this phi naught, if we follow this route, first apply phi naught and then apply exp, then this is equal to f of x. But there is a unique function with these two properties, so this phi naught is equal to f tilde. Now we can follow the same procedure and we can show that phi 1 is equal to g tilde. Now let theta naught of t is equal to f tilde of 0 t. Okay, now what is e raised to power 2 pi iota theta naught? So this is equal to e raised to power 2 pi I f tilde of 0 t. So according to the fact that e raised to power 2 pi I f of xt is equal to so this is f tilde, so this is equal to f of xt. So using this fact, this is equal to f0 t, and which is equal to f of 0, which is equal to g of 0, which is equal to 1. Okay, so by a similar argument of uniqueness, okay, so the same kind of argument that we used to show that phi naught is equal to f tilde, so we can use the same argument to prove that this theta naught is equal to 0, because this theta naught is going to be an integer value, and because this e raised to power 2 pi I theta naught is equal to 1, and using the similar properties, we can see that this theta naught must be equal to 0, because this is going to be an integer valued, and that integer is going to be 0 only. So similarly we can define by taking this x to be equal to 1 and theta 1 of t is equal to f tilde of 1t. So define this c to be e raised to power 2 pi iota theta, which is equal to pi iota f tilde 1t, which once again is f of 1t. So let me say again, this is using the fact f tilde of xt is equal to f of xt. So using this fact, we have this thing, so which by the definition of homotopy, relative homotopy, since this capital F is homotopy of f and g, so for each so for whenever x is equal to 1, so in other words, what we are saying that these endpoints are fixed. Okay, so this is 0 and this is 1, so whenever x is 1, f of 1 and g of 1 are going to be the same. Now e raised to power 2 pi I e raised theta 1 is constant. Okay, so because this is f of 1, also theta 1 of 0 is equal to f tilde of 1. So why is that the case? I'm sure you can see that theta 1 of 0 is equal to f tilde of 1 0. Okay, so which is definitely equal to f tilde of 1. Okay, so we have already seen that. So we can lift c to a function from I to r f tilde of 1, and once again now we are using the same lemma over here, and we are using it for the function theta 1, and we are saying that this theta 1 is a function, is basically a lifting of a function, and so once again applying the same lemma, we get that so f tilde of 1t is equal to theta 1 of t is basically equal to f tilde of 1 for each and every value of t. So that proves that this f tilde is homotopy of f tilde and g tilde, and it's relative homotopy with respect to this, and that's why we had to prove that theta naught is 0 and theta 1 is f tilde of 1. Now the above corollary shows that if we have two homotopic functions F and G, then their winding numbers are equal. So why their winding numbers are equal? Because we have seen that what is a winding number. So given any function, if f tilde is the lifting of f, and given any function g, and g tilde is the lifting of g, then this is equal to this. So f tilde of 0 is basically 0. So we have already seen it. And similarly g tilde of 0 is 0, and f tilde of 1 is equal to g tilde of 1, because they are relative homotopic. Okay, so given any continuous function between these two pointed topological spaces, then we can define the degree of f to be equal to f tilde of 1. So where f tilde is the unique lifting of f, with f tilde of 0 is equal to 0. Okay, so in other words, we are taking that t naught to be equal to 0. Okay, so we have to take this t naught, and if we fix this t naught to be 0, then that lifting is unique. Okay, so that's how we define the degree. So here e raised to power 2 pi I f tilde of 1 is equal to f of 1, of course, because f is equal to e raised to power 2 pi I f tilde of x. Okay, so at x is equal to 1, this is equal to 1. So f tilde lies in the kernel of homomorphism. Okay, so once again, if I'm getting, okay, so this is f tilde, this is r with 0, and these are the points of S1. Okay, so basically when I apply when I calculate 2 pi I f tilde of 1, then I get 1 eventually, so starting from here to here. So in other words, this f tilde lies in the kernel of homomorphism of xp, because I'm getting identity. Okay, so I'm getting identity eventually. So if I'm getting identity in the circle, then this f tilde must be integer over here, because the kernel of this exp are the integers of R0. So this f tilde must be an integer. Okay, so f tilde is an integer, and so that's why this degree is going to be an integer. So degree of any continuous function between the pointed topological spaces I dot to S11 is going to be an integer. So far what we have calculated, so given any continuous function between x naught to S11, we can calculate the winding number of this function by getting its unique lifting, and so that winding number is also an integer. So we have a way of associating loops. Okay, so in particular I can take this x naught to be I naught, okay, and goes to S11, which by definition is a loop inside S11. Okay, so in particular I can consider these loops, and these loops will have a unique lifting f tilde, and so I can calculate the degree of, or the winding number of this function f, and by defining this function d using this winding number. Okay, so we have the expression that the function d from pi 1 of S11 to z given by f goes to degree of f is an isomorphism. So now why this is well defined? So this function is well defined because we have seen that if f is homotopic to g, then they have the same winding number. So this pi 1 of S11 is basically the class, the path classes of all continuous functions or all loops inside this circle. And if two loops are homotopic, then they are going to have the same winding number. So there is no problem. This d is well defined on the classes of pi 1, and this d is taking any loop to its degree. And now we have this result that this map d is an isomorphism. So if it is an isomorphism, then we can say that the group, the fundamental group of the circle is just z. the group of integers. So how this is onto map? So can we find a given any m belongs to z, can we find a function having this winding number m? Of course we can find, we have seen in the example. So for example in this case we can find a function with winding number 2, and we have also observed that taking this f tilde to be mt, I'll be getting winding number as m. So basically I can take this to be z raised to power m, or in particular I can take it to be e raised to power 2 pi iota mt. Okay, so considering the parametric form of the circle, so basically this f is going to be a function from I to s1. Okay, so we can also write it in this form. So we have a function and so this degree d, okay, so this map d is onto map because for every integer there is a function with that winding number. Okay, so how to show that it is one to one? So consider a function f which goes to 0, in other words a function f and which is basically element of this pi1 of s1. In other words, it's a closed path or loop in s1, and the degree of this loop is 0. Okay, so the degree of this loop 0 means f tilde of 1 is 0. So remember that we have calculated for any loop which is a continuous function between these two pointed topological spaces, there exists a unique f tilde, and we have taken this t naught to be 0, and this is the map exp, and we can calculate the winding number by f tilde of 1. So if the degree is 0, which means the winding number is 0, which means f tilde of 1 is 0. Hence f is a closed path in R at 0. So why this is a closed path? Because we have also seen that f tilde is a continuous function, and f tilde of 0 is 0 and f tilde of 1 is 0. So in this case, if f tilde of 1 is also 0, then we have a continuous function with the same initial and final point, so which means it's a loop in R of 0. Okay, so we also know that if we have a continuous function between two spaces, then this induces a map between their fundamental group, and this map is relatively simple. So how to define this map? So given any point of this space, so we can just apply exp at that point, and we can calculate the class of that. So the continuous image, so in short, so the idea of this homomorphism is that the continuous image of a loop is also a loop inside the other space. So that's why we are taking loops from this space to the loops in this space. But the point is R1 is convex, so pi1 of R1 of 0, so with this base point, so this is going to be trivial. Okay, so we have a loop inside R at 0, and which is trivial. So in other words, and this is also a homomorphism, so homomorphisms takes zeros to zeros, so which means that this f tilde, which is a loop inside this space, goes to e raised to power 2 pi I f, and which is equal to basically the f. Okay, so we have seen that this f is equal to e raised to power 2 pi I f tilde. Okay, so this is f tilde, so this is equal to f, and we have also seen that how we define this homomorphism. Just take any loop and apply exp on f, so in other words e raised to power 2 pi I f. Okay, so in this case the function is f tilde, so we have this which is equal to f, so the path class of f. Now this f tilde, so this is 0, and this is also a homomorphism which takes zeros to zeros, so which means that this is 0. So in other words, if the degree of f is 0, then f is 0, which means the function is 1 to 1. Now in the last part of the proof, we have to show that this map D is basically a homomorphism. Now how to show that this D is homomorphism? So take any two points of this fundamental group, and we have to show that degree of f star g is equal to degree of f plus degree of g. So how to show that? So basically these are elements of this, so these are loops inside this circle. Okay, so we can calculate their degree, so we can lift okay, so lifting of f is f tilde, and let's say lifting of g is g tilde. So using these f tilde and g tilde, we can find the degrees of these f, so by calculating f tilde of 1 and by calculating g tilde of 1. So let's say f tilde of 1 is equal to n and g tilde of 1 is equal to m. Okay, so we now want to calculate basically degree of f star and g star. Okay, so let h tilde is lifting of f star g. Okay, so if we want to calculate the degree of f star g, then we should know the lifting of this. Okay, so that we can calculate the degree of f star g to be h tilde of 1, and we want to show that. Okay, to show is h tilde of 1 is equal to m plus n. Now we can define our function gamma is equal to n plus g tilde of t. Now we claim that f tilde star gamma tilde is a lifting of f star g. Okay, so if it's a lifting of f star g, then we have to check the conditions of our main lemma, and you can easily see that this is a lifting of f star g, and also we can calculate f tilde star gamma tilde and its value of at 1, so we can easily see that this is equal to n plus m. So that proves the results. So we have proved that the fundamental group of a circle is basically group of integers. So the proof of next theorem is not part of our lectures, but it's a very important theorem which can be proved with the results that we have seen today, that every non-constant polynomial with complex coefficients has a complex root, and as an easy consequence of this theorem we can see that every complex polynomial of degree n has exactly n complex roots. Okay, so this is the end of our lecture. Next time we will be interested in homology. So this is the end of the lecture. Thank you very much, and Allah Hafiz.